بس عفوا صوتك ما واضح.
واصل.
ما جاي بالنسبة لصوتك.
please لي اسمح لي. الصورة ما واضحة.
الصوت واضح هسه؟
اوكي تمام هسه واضح الصوت.
صوت. speaker.
اوكي.
Good afternoon, everyone. First of all, I would like to start by saying that I truly regret that I was not able to join in person into Basra. And this was due to the last minute emergencies that I had. Plus, I would like to thank everyone to set up this meeting over Zoom. So this part of the session, we're going to see the modern predictive systems that we have been seeing in the oil and gas industry for the past like 4 to 5 years, and what you should expect from them, and basically how they behave in certain circumstances. Before we go ahead and start these topics, it's really good to understand what we're going to see today. So the first thing that we're going to see is the physical phenomena that dominates oil and gas industry. We have to understand what phenomena we're dealing with. Otherwise, we don't know what problems we're dealing with. Second of all, I'm going to show you the classical solution to existing oil and gas problems, some modern solutions or modernish solutions. I should going to show you what machine learning can do for us, what is a genetic learning and deep learning, and some introduction to physics learning. In introduction to physics learning, I'm going to show you a live example in Python how we can discover physics using existing oil and gas field data. Plus, I'm going to show you the integration of modern prediction systems with the classical solutions that we have in the oil and gas industry. Plus, I'm going to show you a slide that summarizes all the technologies that you need to get started in this domain. So the oil and gas industry, it's a really unique combination of 3 physical phenomena, which is the conservation of mass, the conservation of momentum, and the conservation of energy. And we can see all of these phenomena and all of these rules basically everywhere in the industry. We see them in the flow lines, in the wells, in the reservoirs, in the vessels, in the tanks. You name it, we see it there. Sometimes we get combination of 2, sometimes it's combination of 3, but mostly it's just combination of 3 of them. And oil and gas industry and petroleum engineers usually are in the intersection of these 3 phenomena. Now, why I am showing you this? Because in order to truly understand how your system behaves, you have to be able to solve all of these problems and basically all of these equations at the same time. So if we take a look at the general forms of these equations, we find them. It's constitutes of multiple parts variables, and most of these variables are unknowns. These variables need lots of data in order to get solving them. So that's why it's not straightforward to solve these problems. That's why oil and gas industry early engineers started to simplify these equations. For example, instead of solving this for 3-dimensional problems, we started to solve them for just point models with no dimensions, and then we basically started to solve it for 1-dimensional problems, and then we started to solve them for 2-dimensional. Sometimes we leave out the energy transformation or the change of energy in order to make things simpler. This is especially true for conventional reservoirs. Yeah. However, no matter how you take a look at these equations, it's always really, really, really tough to solve. Usually, you need some form of industrial simulators to solve these. But most of the time, our data is not enough in order to start to incorporate these types of solutions. And you need really high-level mathematical knowledge in order to incorporate these in some of the problems that you're having. So that's why early oil and gas industry adopters actually they started to solve oil and gas problems by either they basically from lessons learned from the field, or they used empirical methods, and more modernly they started to use mechanistic method, which basically relies on some sort of physics inside a certain facility. So one of the earliest solutions in oil and gas industry, it's Darcy's equation. And the Darcy's equation, it dates back to 1800 by a French civil engineer. Yeah, the problem with the Darcy equation, it's not that it has limitations like the empirical basis, the incompressibility, single phase flow. There is no wettability included. Yeah, these are all apart. But nowadays, if we take a look at Darcy's equation from the modern data science tools, we will see that Darcy's equation, it's based on very limited data. So the decisions that we make, basically, it's ranging from millions of dollars to sometimes to billions of dollars. It's based on an equation that's built on, are you ready for this? It's built on only on 10 data points. Yeah, this is how Darcy's equation was built. It was 10 data points that dating back to 1800s, a straight line fit that basically then transformed into Darcy's equation. And then we have in the early 1900, we have Muscat that take this equation and then introduced the concept of fluid properties in terms of flow, of course. Yeah, so just take a look at how limited this equation is, because we are going to see the modern solutions to these types of problems that are not behaving as you're expecting. Another common problem in oil and gas industry is predicting, for example, the corrosion. Predicting corrosion, it's really common thing that we usually do in oil and gas industry. One of the most common equations, or more properly correlations in the industry, is known as the API 14ERP. This equation basically shows you, basically it calculates a value for you. This value is called the erosional velocity limit value. Based on this erosional velocity value, you will compare it with the actual velocity you have in the pipeline or even in the well, and then you know if you're exceeding or not exceeding the erosion limit. But yeah, there are some caveats of this equation. For example, it's only designed for single phase flow. There is no alloy consideration. Okay, so basically this equation only works for carbon steel. And you have to lump everything up because there's a single density required, and there is also some problem with the C. People disagree usually on what the value of C is. Plus, it does not take into consideration any electrochemicals. Okay, but everything can change if we start to adopt to AI. Okay, so now it's time to actually to question one thing, and this is this question I ask this question a lot, especially during the sessions I deliver. Is the question goes like this: can you think of any mathematical representation or any mathematical correlation in oil and gas industry that can return the type of problem you have? For example, let's imagine there is an equation in the industry that can basically tell you if you're working with seized wells, or there is some type of skin factor that happened to your well, or some type of label to your problem, like your pump is tripping or your compressor is overheating. Now, do we have an equation that looks like this in the oil and gas industry? Just think of this. Usually the answer is going to be no. Mathematical equations, they don't return text values. Okay, so just keep this in mind. Mathematical equations tend not to return text values. The best it can return categories like zeros and ones, and that's it. They cannot do more than that. So because this problem, it's a unique problem that we have been having in the oil and gas industry for the past decades, and the solution to this problem usually lies with AI. And you will see how we can solve this problem as we progress in these slides. Okay, so Now, once we understand the classical limitation of oil and gas industry, it's really good to know how we can solve these. So we can solve these with the modern data science or the modern stack of technology we have in the data science. So data science, it's a really unique intersection of three things: computer IT, mathematical science, statistics, domain knowledge, and basically one of the most important things you have is you have to have the domain knowledge. Otherwise, it does not make any sense. So the modern data science, it's a big umbrella of different tools and methodologies that allows us to do various of things. For example, we can do analytics, we can do predictions, we can do system experts, we can do lots of things. And everything we can do nowadays, it's under the umbrella of modern data science. Now, the most important thing that you can do in data science is prediction. Prediction is basically to understand the behavior of something or being able to predict the behavior of something, either that happened in the past or that's going to happen in the future. If something that happens in the future and we want to know what that's going to be, usually we call this forecasting. But yeah. This is basically what prediction means. And prediction is the ultimate goal that we seek in oil and gas industry because we want to understand what's going to happen in the future based on what we have been experiencing in the historical time frame. So some of the predictions and the forecasting methods that we have in oil and gas industry, we have the heuristic methods. So these methods are based on some certain hard parameters. And these parameters, they don't have any scientific backing, and we are going to see these. We have something called rule-based system. Rule-based system, it's widely separated in the oil and gas industry, and we are going to also see an example on this. We also have some statistical methods or some stochastic methods. And finally, we have the AI, machine learning, deep learning methods. Okay, so we are only going to present two of these. For example, heuristic methods are methods in oil and gas industry that don't have any scientific backing. One example will be setting the overbalance for a drilling well, for a well being drilled at any given section from 100 to 300 PSI gauges. So this number works very, very well in most wells, not in all wells. In most wells, it's very good. But yeah, this does not have any scientific backing to it. The only thing we know this works. Okay. So another thing is to develop some certain parts of the fields based on some left, let's say, or some ultimate recovery that you want to achieve. For example, more than 50% of the average of the field. Maybe you want to include some golden ratio like 1.6 of the field. So no matter what you do in these types of assumptions, these assumptions are going to be heuristic method of modeling. It's basically, it has some truth to it, but it does not mean that it's 100% scientific. The next thing that we have been seeing in the industry a lot, this is especially true from the late 60s to the nowadays, which is rule-based systems. Rule-based systems are predetermined systems that goes over a specific workflow. We can see these workflow a lot in softwares like Pipesym, Prosport, Gap, Olga, well test packages, reservoir simulation tools. This rule-based system actually does not only exist in oil and gas industry, it basically exists in all the industries that require some sort of calculation. And the problem with the rule-based system is these rules are predetermined. These rules do not change. And if you want to change the rules, there is a problem that's going to happen with the system. Most often, even the system, either the system can fail or the calculations can go wrong. Okay, so either way, it's a really bad situation. So just think of this rule-based system is what we have currently, especially in the classical solutions to the problems we have in the industry. Now, once you understand these limitations, it's really good to know what AI can bring or what AI can bridge. Before we tackle the types of AIs and the types of the algorithms we have, just keep in mind AI can help you to solve two types of problems. The first type of problem is already existing problems that you can solve with classical methods, okay? Plus a new categories of problems that are not able to be solved with the classical methods. So these two things can be tackled together. So AI can do lots of things for you. It can be used for operational parameter prediction. You can use AI to predict what's going to be drilled ahead. So you want to predict, for example, 3 feet or 10 feet or 20 feet, what's going to come up, what's the next lithology, what is going to be the porosity, what's going to be the probability of the pipe, the drilling pipe to be stuck. Okay, so all of these types of things. You can detect events. You can even detect events very, very early. This is especially true if you're working with ESPs. You can identify lithology, you can discover patterns, you can extract data from PDFs. You can do lots of things. And the most common thing that's nowadays is being pushed towards, it's something called RAG or RAG. This is basically an expert system that has the capability to summarize PDF documents for you. And this is especially helpful whenever we're working with drilling reports. So these two problems, for example, these are mislabeled. So the first two problems, which is the operational parameter prediction and the drilling ahead, these are usual regression problems. And the lithology identification and pattern discovery, usually these can be classification problems, or the early event detection and event detection, these can be classification problems.
Yes.
We will see what regression and classification means. So what are the types of AI we have? Well, currently we have at least 3 or 4 types of AI. We might have different types of AI as we progress in the future. But the main one, or the most common one nowadays that you see these a lot in the papers, this was very significant from 2010 to 2020. So in the past decade, this was very important, which is the classical machine learning models or the classical machine learning algorithms. So these types of algorithms basically will take some sort of data, and then it will start to predict and understand the patterns within these data to predict some certain things that you want to understand. It can be wellhead pressure, it can be bottom hole pressure, it can be reservoir pressure, it can be any parameter that you have already captured in the field and you want to predict its performance. Okay, so in the classical machine learning and most of the type of the calculations that we can do in the machine learning actually relies on 3 important tasks. The first task is called regression. Basically, you have number inputs and then you have number outputs. You have classification. Classification this is the most important task that's irreplaceable. We don't have anything synonymous to this in oil and gas industry, where you have some operational parameters. For example, you have some compressor parameters, and in front of each compressor parameter, you have the events that's related to some type of problem. So if you want to predict or if you want to relate the numbers to the event itself, you have to use classification. And clustering, this requires extensive domain knowledge because you will take some data with no output, and then you will generate an output, or you generate basically some pattern based on it. And then you will start to analyze these patterns to see why the system came up with such a result. Okay, so this is very fun, to be honest. Now, what are the problems with the classical machine learning? You have to understand the problems before you even go and progress. I see lots of many researchers, they jump directly to deep learning, which is not correct. You have to understand why the classical machine learning fail in order to understand what tools you're going to adopt. So there are many problems with the classical machine learning. So one of the problems is the extrapolation problem. Okay, I will show you how this problem can be solved. Another problem is the lack of mathematical representation. I have been asked countless of times, can we return equations from machine learning? So the answer is usually no, you cannot. There is one exception to this, and I will show you that. And I will show you the proper solution to the mathematical representation. So the key idea is if you train a machine learning model, the machine learning model cannot return a mathematical equations. There is some certain rules that you need to understand about this. Okay, so even in deep learning, you cannot return equations. I will show you how to do that properly. Plus, if you work with machine learning models, which is usually called tabular machine learning models, these types of models cannot work with gridded data. So if you have some certain gridded data, like you're working with topology, maybe you're working with maps, maybe you're working with multiple wells being correlated together, maybe you're working with seismic sections, these models cannot basically process this type of data very, very well. It requires extensive data transformation. I am not saying that they cannot absolutely work. It can work with these types of problems, but they require extensive data manipulation. Okay, so that's why geospatial problems are really one of the weak points of the typical and classical machine learning models. Now, of course, the machine learning model, if it cannot work with grid data, then it cannot work with three-dimensional data as well, like reservoir cubes, like NWRs or the near well models. So we cannot work with these types of models as well in the machine learning. And I will show you where this comes into play. Now, let me show you how to solve some of these limitations. Let's start with the extrapolation. You can extrapolate a model, a machine learning model, but under one condition. You have to use something called multilinear regression. Multilinear regression, it's a type of machine learning that you want to relate a certain parameter to like multiple other parameters. We know these as features and targets. And in mathematics, this is known as dependent and independent variables. So the idea is, let's say, for example, as this image shows, let's say we want to predict the bottom hole pressure, okay, in terms of wellhead pressure, wellhead temperature, the casing pressure, the flow rate, water cut, gas oil ratio. No matter what it is, you can predict it or you can add it because there is no limitation. The limitation should come from different places like domain knowledge, some statistical restrictions. Yeah, so there are limitations will be in place, policies enforced by the practitioner, but the machine learning usually does not enforce you on certain type of oil and gas inputs. Okay, so you are free to input whatever you want, but you have to be very, very careful. It has to resonate with the model itself or what you're trying to achieve. So the key idea is if we take all of these parameters that you see on the left-hand side and try to plot it on the same plot, we can see there is a certain line that fits into each one of these series, okay? So now, how can you relate all of these together? You can relate them by applying something called MLR transformation or multilinear regression transformation, where you will assume that, yes, it's an assumption, you'll assume that in order to calculate the bottom hole pressure, it must be a function of wellhead pressure multiplied by its own weight, tubing head temperature multiplied by its own weight, gas oil ratio multiplied by its own weight. In oil and gas industry, we call these tuning factors. Yeah, in machine learning, these are called weights. Okay, and of course, you will have some form of a bias, some form of an error term in order to make this work properly. This model has the capability to extrapolate. That's why I'm showing you. Otherwise, you cannot extrapolate. Other models like random forest, extra trees, XGBoost, light GBM, all of these models cannot extrapolate. So you have to keep that in mind. Now let's move to the next problem. I'm going to show you some of the problems that you can have with extrapolation. Now, this is an actual field data. This data shows you two things, okay? So you have the green curve, which is the historical production data, and you have the red curve, which is the predicted historical data using something called CRM. CRM is short for capacitance resistance model. This is one of the analytical models that you can use in the reservoir engineering domain, where you can relate producers, injectors together to see the relationship between them. Okay, so this example illustrates that. Now, if we take out the prediction from the CRM, which is the red line, and introduce the prediction using machine learning, we can do that. And basically, to be honest, it's way more accurate. But keep in mind, if you provide not enough data, the model cannot extrapolate. And this is exactly what's happening in this red arrow. You can see the model flattens out. It means that, well, you're trying to predict outside of the range. Now, this is one of the main issues of the machine learning, and I will show you how to solve this. Now, this can be solved in a couple of ways. So the first way to do it, which is not always possible, it's to include more training points. So if we go past and add some couple of more points to this, we can see we can fairly accurately start to predict the behavior of the producer well in terms of how much barrels of water we are injecting in the nearby well. Okay, so that's the case. This is one thing, is to add more data to it. Okay, so add more data, but this is not always applicable. Now, let's move on to the next one. How can we basically extrapolate our model. Now, in order to extrapolate the model, you need to understand the physics behind your data. In the earlier slides, we said that these equations usually are really complicated to be solved for a certain problem unless you have lots of assumptions. And even at that stage, well, the solution is not guaranteed. You can try, it might work, but it's not guaranteed. Okay, so that's why there is another caliber of machine learning models, or there is another caliber of AI. It's called genetic programming. So, what is genetic programming? Genetic programming, it's one of the least used and the most underrated AI models that you can see. So, genetic programming, it basically takes the idea from Darwin's evolutionary theory, where it says that, for example, living things can change, can have some form of evolution, and basically the genes we have can mutate or it can change themselves. So mathematicians, what they did, they basically they took this idea and then converted this into mathematical representation. Now they started with this assumption: we have two data columns. Okay, so we have the column X and we have column Y. Okay, or let's say that we have the wellhead pressure and the PWF, or we have PWF and we have the reservoir pressure. Okay, so we want to calculate the actual reservoir pressure based on the PWF or the PWS, the static one. Okay, so how can you do that? You will start first with linear regression, and then the equation starts to change itself. It starts to mutate. It will start to shift and change the position of the PWF. Maybe it sometimes once it's going to be on the numerator, and the denominator, maybe it goes under the square root, maybe it goes to the power. So this is called mutation. Sometimes you will cross over. Sometimes you use different paths or different equations, combine them as a crossover to create one physics or one equation that represent your problem. Okay, so this is known as genetic programming. Okay, so genetic programming has the potential to produce not just one equation, but a really complex set of equations. I have an example I will show you, a Python code that does that basically for you. So you'll start from the simplest equation to the really complicated equation. The more complicated the equation is generated by AI, the more accurate the solution is, but it's really complicated to implement in the field. Okay, so whenever we're working with these types of problems, usually there is some trade-off between the accuracy and complexity. So you have to make the trade-off. Let me show you an example. So this is an actual example from Middle East. This is a relative permeability study from one of the cores in Middle East. So basically what we're trying to do in this example, we have two curves. We have one curve, which is the green curve. This is basically the Corey's calculation or the Corey's fit to the historical data or the lab data. So the lab data are the real data, which are these blue points. And you can see the Corey equation that basically fits very nicely into it. So there is no problem. Corey's equation needs some tuning. Usually these tuning can be either manual or it can be calculated using some type of curve fitting, like curve fitting that you have in Python or the curve fitting that you have in Excel. Now, this is the classical solution. Now, let me show you the more modern solution. If you want a better fit, you have to discover the physics behind these data. Basically, the physics behind this data does not need to come from one core example. It can come from a set of cores or multiple cores from the same formation for the full field. You can convert this into a single equation that fits everything together. And this equation is discovered by using genetic learning. Okay, so now you see these two sets of equations, which is the relative permeability of water and the relative permeability of oil. These are discovered by AI. AI is suggesting that these two equations, actually, they are not just fit good, they are actually even better than the Corey's equation because the residual error is much lower than Corey's equation. So this is one way of basically applying this. So another example will be, which is in my opinion, this is one of the most important examples that we can do in genetic learning. It's calculating the bottom hole pressure. So to calculate bottom hole pressure, we know that bottom hole pressure relies on multitudes of parameters. One of these parameters usually is the PVT properties, and the PVT properties, of course, it's different from one well to another because the operational parameters is different. Okay, so what happens if you take, for example, the wellhead pressure, maybe the flow line pressure, maybe some properties about the oil, and then basically put this into AI and try to get some equation from it. And this is what I've done. So this example basically shows you unconventional gas wells where I have multiple gas wells being trained and telling an AI basically suggest an equation for us in order to calculate the bottom hole pressure in terms of wellhead pressure and other volume ratios. Okay, so this is the SPE dataset, which basically contains 52 wells. I have taken like 30 wells, which are gas wells, and believe it or not, genetic learning can suggest just one equation that can fit everything at the same time. And this is what the equation looks like. Okay, so basically, the genetic learning can return two things. Either you get equation from it, or you can get a model file. Either ways, it's just fine. It works the same. Okay, so if you're looking for equations or you want to discover something from a physics from your data, well, genetic learning is really, really good starting point. Before we go to the neural nets, let me show you one example of genetic learning in Python. So we have the same example, but this time for just one well. So we are calculating PWF for one well using genetic learning. And you can see the red one is the model discovery. So the model discovered an equation for us that fits this data very, very well. And if we zoom into the data, you can see the accuracy is really good. And it's within, it's less than 5% of error. So now if we want to see the results or the equation that was calculated, we can get the best fitting equation, which is this one. And we can, of course, format the numbers as well. But if you're interested in the full range of equations that was discovered by this model, so what you're going to do is you're going to iterate through the equations that were discovered. And let's run this. There we go. Now, this is the full range of equations that were found by the model. Of course, the simplest the equation, the less accurate it is. As you go down, as the complexity increases, the more accurate the equations become. But they are really going to be really hard and really complicated. And the complexity of these equations, we can control it. We can make it simpler in complexity, or we can make it really, really deep in complexity. You can add more parameter to this. You can take some parameters out from this, and basically it's 100% controllable. So this is basically one of the ways genetic learning can be used to discover equation. This is especially true. This is especially true whenever you're working with things that don't have any correlations yet. For example, if you're working with, for example, laboratory results on emulsion treatment, usually we don't have like really hard set rules on how to treat some certain emulsions. But if you take the emulsion temperature, the strengthness of the emulsion, the type of the materials you're using, the dosages and whatnot, I believe you can discover some physics from it. It might not be very accurate, but it's going to be a good starting point. Now, let's move on to the next caliber of AI, which is, it's a more complicated one. Sometimes the machine learning models, they can work very, very well, the classical models, but they cannot predict really, really, really deep patterns. Now, in order for these deep patterns to be discovered, we need to change our models from simple classical models into something called neural networks. Neural networks, they supposedly mimic how humans think, and you can connect multiple neurons together. We can have simple neurons as called SLP, or single layer perceptron, where you have one neuron. One neuron, basically, it's like one brain cell. You can have some input and then you have some output. Okay, we can have a more common one, which is MLR, or MLP, multi-layer perceptron. MLP, you can even find MLP in, I think, in TechLog. It also exists. Multi-layer perceptron, basically, you have multi-neurons, multi-input, and then basically you want to predict one output. It's really similar to the task that you would do with multilinear regression, but the structure and architecture is different. Now, these two things can do exactly the same things that the machine learning does, but now starts the different part. You have another caliber of models, which is called the sequence prediction models or recurrent neural network model. These models have the potential to predict what's going to happen in the future based on some past observations, because it will understand how these sequences change with time. So it's very similar to time series analysis, but it's way more accurate. So if you know, there is a domain in AI, it's called NLP or natural language processing. Natural language processing is basically built on the same idea, or the idea of the recurrence, or training something that remembers data from its past. So this is what it means. Now, the next caliber is one of the most important ones, especially in geophysics. It's called CNN, or convolutional neural networks. Convolutional neural networks, it's the only neural network type, and it's the only AI type that can work with gridded data, like two-dimensional data, three-dimensional data. Basically, was not designed for oil and gas industry. This was designed to analyze images, pictures, like a picture of apples, picture of cats, mouse, and classify these and understand how these look like. But oil and gas industry people shifted these algorithms and started to adapt them mostly for seismic profile analysis. You can also do some topology analysis with this. By the way, I know some people who buy and sell volumes of so basically they are brokers in oil and gas industry. They purchase barrels of oil and sell them afterwards. They base their work on convolutional neural networks, because what they have done is they have satellite images of the tank depots or the tank farms. They know based on the shadow of the tank if the tank is full or not. So they analyze these things and they understand if the reserve is going down, or sorry, the surface reserve is going down or it's going up. So basically they decide to sell or buy based on this algorithm. So one of the things that you need to do, it's the duo of the classical and the modern integration. So how can you integrate the modern AI with the classical oil and gas industry? So for that, we have lots of things. You can integrate the outputs of a certain simulation software with the models that you have already existing in the AI. This is known as a proxy modeling. Some companies are already doing that. If you don't have a platform, you can also use Python for this. Some other integration would be, it's the same thing as proxy modeling. You can extract data from these simulation tools using Python and then push these tools, or sorry, push these results into smart model. Smart model will start to find patterns and start to behave like your simulation tool. Okay, of course, it's going to be limited. It's not going to be as accurate as the original tool, but this has the potential to solve the licensing problem for you, because sometimes we have restriction in licensing. So basically, if you train a model to act like a software, maybe this can eliminate some of the license usages that you need to purchase. One more thing that you can do for AI, or some of the key use cases, it's to predict the liquid loading in gas wells. We have lots of methods. We have